This is the story of an experiment carried out at the Eurocontrol Experimental Centre concerning the possibility for ground-based air traffic control systems to offer pilots greater freedom to choose the routes that they would prefer to fly instead of being constrained to fly the current route network, which does not conform to modern air transport criteria, and in particular does not take account of the investment made by the airline operators in modern avionic technology. As can be seen from these maps, existing routes consist of lines joining fixed geographical locations, and air traffic authorities, in facing traffic demand, have multiplied both the number of points and the number of route segments joining them. It can be seen, however, that a flight between any pair of airports is unlikely to be an economic straight line in the circumstances. Before seeing how the experiment was mounted and carried out, let us see how it was that the situation arose. In the early days of civil aviation, navigational aids were rudimentary and consisted mainly of radio beacons which air navigators could tune in successively and fly towards. This caused aircraft to concentrate on such locations and led to the need to have ground-based authorities to implement control systems to prevent aircraft interfering with one another or even colliding. A useful illustration of the problem is the development of road systems as traffic increased. Initially, travelers followed the easiest path between any 2 points without much consideration for efficiency. Later on, traffic volume caused the introduction of more direct and more efficient routes, but tended to concentrate traffic at the route intersections. Road designers reacted by introducing expensive methods of flow control at these intersections in order to minimize the chances of collision and to keep the traffic flowing. The air traffic control problem was, and still is, identical. The basic ATC rules are concerned with safety to avoid collision and expedition to keep the traffic flowing in an economic way. The fixed and named identified geographical location is the cornerstone of the current air route and air traffic control system. At the principal nodes of the route network, air traffic control authorities have installed modern navigational aids of the VOR-DME type to provide pilots with range and bearing information. In the cockpit, the pilot uses his VOR-DME instruments to determine his ground position and tunes them in successively as he proceeds along his route from beacon to beacon. On the ground in the control centers, the controller's traffic displays are images of the fixed or predetermined route system. They may be flight progress strips, or electronic data displays, or even radar screens. But all of them are based upon interpreting aircraft routes as sequences of named and fixed points. Providing that aircraft avionic fit is only to the level of, say, twin VOR-DME, the air and ground systems are compatible with one another because both find it convenient to use a point-to-point route system. The system becomes unbalanced, however, when a high-technology avionic fit exists, because for the aircraft operator, it is no longer either convenient or economic to conform to the extra route lengths which are induced by the point system. Such an avionics system is the appropriately named flight management system. Amongst its microcomputer-controlled subsystems is the navigational computer, responsible for carrying out the route part of the pilot's flight plan. Using the current plan and its local database, which can contain up to 30,000 route points, it can automatically select and tune the ground aids appropriate to any route, direct or otherwise, and issue commands to the autopilot to take the appropriate action to follow it. The FMS has fundamentally changed the traditional role of the pilots. The new role is that of the avionics systems managers, who decide the nature of the current global objective and communicate it to the FMS using the keyboard input device. The FMS then coordinates the actions of the various avionics subsystems to achieve that aim. In respect of route flying, this means that considerable economic savings can be made by proceeding directly from departure to destination without having to conform to the point-to-point infrastructure. This is what is called the free route concept. To be usable as a concept, the ground-based ATC system must be capable of adapting itself to the airborne capability. And so the conduct of a preliminary experiment was confided to the Eurocontrol Experimental Centre at Bretigny-sur-Orge with the general aim of seeing if such an adaptation was feasible. The centre possessed powerful real-time simulation facilities, particularly in respect of electronic traffic displays for controllers. And the basis of the investigation in the circumstances was evidently a question of how to present free route traffic to controllers and permit them to maintain safe and expeditious flow. The first task was to choose an airspace suitable for the experiment. The choice was based on finding an area in which the benefits of a free route system would be apparent for airspace users, but the nature of the air traffic control problem would be distinctly different from that of the existing system. Several European areas which presented potential bottleneck problems were considered. Strombel in the United Kingdom, Spijkenborg in the Netherlands, Frankfurt in the Federal Republic, Olno in Belgium. But the final choice was Nantes in western France. The experimental scenario was then developed by assuming that the whole of France had become a free route area, but that the fixed route system still existed elsewhere. This assumption fixed the entry and exit points to the complete France FIR-UIR. The free route system was then constructed by joining the entry-exit points by straight lines and excluding all routes which did not enter the existing limits of the Nantes sector. The result can be seen to be quite different from the current system in the Nantes sector, which essentially routes all traffic via one point, whilst the free route system produces multiple point intersections. The problem of the traffic displays was to communicate to controllers exercising the traditional roles of planning and executive traffic information related to multiple flight profile intersections spread across the sector, with a consequent risk of loss of separation at points which could not be named. Given only the entry and exit times, points and levels, plus a set of rules defining planning separation standards, the computer system could detect separation infringements in area terms, but the display input system had to solve the problems of enabling the controllers to appreciate the nature of any given infringement and to resolve it by profile modification if this was possible. This resulted in three principal display innovations. The first concerned the planning controller. As all routes were straight, planning control could only be exercised by vertical profile control techniques. This led to the adaptation to the free route problem of an earlier experiment called CAPE, or the Computer Assisted Planning Experiment, reported in EEC report number 185. Essentially, the planner acted on a traditional first-come, first-served basis as aircraft were notified to the system. At flight selection by the planner, the vertical profile of the aircraft was displayed on the basis of its flight plan, including climb or descent as appropriate. In addition, all potential infringements of separation with aircraft which had already been cleared were shown. The planner, using his professional experience, could then adjust the vertical profile within sector limits in order to eliminate infringements if they existed, and then issue his clearance by informing the computer of his authorized profile. Evidently, however, it was not always possible for him to eliminate all potential conflicts, and so his clearances could contain residual conflicts according to planning standards. Each clearance given by the planner then led to two items of information that the computer had to transmit to the executive controller's displays. The first item concerned executive control of the profile. Level changes could only be expressed in time, as no named points existed, and so the tabular display provided data such as shown in the bottom right-hand corner, indicating that Portuguese 454 from Brussels to Lisbon should climb to flight level 310 at 15:22. The second item involved the communication of the residual conflicts resulting from the planning clearance. This led to a second display innovation, which we will call the conflict risk display. It consisted of a classic orthogonal graph with the x-axis calibrated in minutes of time, future time being at the right extremity and now time at the origin. The y-axis was calibrated using a risk criterion chosen as distance for the purposes of this experiment. Low risk, that is large distance, is at the upper extremity, and high risk or small distance at the origin. A glance at this display then indicated both the degree of risk involved and the urgency with which that risk should be considered. In terms of data position on display, top right meant that low risk was in the future. Bottom right, high risk in the future. Top left, low risk soon. And bottom left, high risk soon, with an evident indication of increasing urgency from top right to bottom left. The display was entirely automatic. It was updated at each clearance containing a residual conflict, and at each minute by moving left to keep the now time at the origin. Two such displays were provided, one for the planner scaled to 30 minutes ahead, the other for the executive scaled to 15 minutes. The third innovation concerned the radar display of the executive. It was evidently no longer possible to have a preset video map. Instead, the video map was computer-generated dynamically as traffic was notified, the routes being displayed at notification to the system and deleted at sector exit. Unlike a classic video map then, the radar screen only displayed routes if they were actually being used, and the route intersections were shown on an area free route basis. The real-time phase of the experiment took place in September and October 1985. The participating controllers consisted both of centre staff controllers, some of whom had participated in the experimental design, and of practicing French controllers from the Paris and Bordeaux centres who had not. The traffic samples used were relatively heavy. Peak traffic in the sector was 20 plus in all directions, with the correspondingly high entry rates for the planner and the executive. The average flight time in the sector being of the order of 20 minutes. Real-time operation provided for situations in which the conflict-free planning clearance failed for some reason, and a radar separation potential conflict occurred. In such cases, the computer system automatically detected the risk using a different set of short-term conflict rules and alerted the executive controller to the situation directly on his radar screen. As this was the first time that any of the participating controllers had ever dealt with traffic or traffic displays totally devoid of named reference points, experimental staff paid particular attention as to whether or not controllers were succeeding to maintain their global traffic pictures whilst maintaining their basic ATC roles of expedition and safety. Details of the conduct and of the results of the experiment can be found in EEC report number 192, but a number of global conclusions can be stated. The principal conclusion of the experiment was that it worked. Just as air crew have adapted themselves to the implementation of advanced microcomputer-based technology in the cockpit, with its associated electronic displays and input devices, and thus liberated themselves from the uneconomic constraints of a fixed-point route network, the experiment showed, in a realistic real-time environment, that given corresponding computer-driven traffic displays, controllers can match the evolution of the airborne capability. It equally demonstrated that without such ground-based technology, the general application of concepts such as free routes will not be possible, and that in particular, ground systems which depend upon flight progress strips appear to be incompatible with the free route concept. No one would pretend that the experiment solved the problem, but it confirmed the hypothesis that the computer-controlled display and input system is the key. It can be said that this experiment was not the end of the story, but only the beginning. It demonstrated the principle upon which ATC systems can be developed to meet the challenge of the economic operation of the air transport system which they serve. Experimental establishments, such as the Eurocontrol Experimental Centre, possess both the means and the know-how to assist air traffic control authorities in choosing the options best suited to their individual systems, and thus help to ensure that economy in the airborne system is matched by economy on the ground.